Okay, so our last topic of study here with solutions is going to be about colligative properties. So colligative means depending on the collection, and so that's directly related to what type of solute we have dissolved in the solvent. Different solutes are going to play a critical role in how a solution may perform in particular situations, and also changes sort of the, when I'm adding that solute to water, I am also contaminating that water with the solute, if you think about it. And the properties of water no longer exist on their own. The properties of the solute and the solvent together are going to create their own unique, physical properties that it could affect things such as boiling point, melting point, etc. So again, that's just what it's discussing here, is that the physical properties of solutions that are affected by the number of solute particles, but not necessarily by the identity of those solute particles. Okay, so we have two types of substances as a refresher. Remember, we have pure substances. The properties of those are consistent across that pure substance. So pure water will always have a freezing point of 0 degrees Celsius. And then we have impure substances. So properties of impure substances will change. And a lot of times impure substances, for what we're going to discuss for solutions, will be the solution that we have made. We have a solute interacting with a solvent now, and so together they're going to have their own unique new freezing point. Okay, so something that we haven't really had a big chance to talk about is, well, we have really actually throughout the year, but I'm hoping you can start developing a picture in your mind of what's going on. But what happens to solutes as they dissolve in solvents? There are different things that occur. So sugar, for instance, has that attractive force with the water, and so therefore dissolves into the water, but it remains together intact as that covalent bond, that sucrose. But salt, on the other hand, an example would be the sodium chloride. It will actually dissociate into ions. So it'll have a positive end and a negative end. So it's like it's pulled apart as it's dissolving in that water while still maintaining its ionic bond. So the question that we want to ask ourselves is, which of these two solutions will have a higher molal concentration? Well, if you think about it, look on the left side for the sugar and look on the right side, and it's sugar. It's 1 mole of sugar here creates 1 mole of sugar in solution. But if you look at the salt one, if you think about how that looks, on the left-hand side we have 1 mole of table salt, and on the product side we have 1 mole of sodium ions plus 1 mole of chloride ions. So it appears that potentially the sodium chloride could have a greater concentration or molal concentration based on the fact that there are 2 particles there in that solution now. So these are just some pictures here to show you what's going on. If we look here, we've got the sugar, it's dissolved, all those little molecules still stick together. On the right-hand side, though, we see the sodium chloride, and you can see that in solution we have a whole bunch of Na plus and Cl minus that are floating around in that solution. Okay, so colligative properties. Colligative properties, again, remember, it's depending on what that solute particle is in the solution. They are directly proportional to the concentration of the solution. And so there's a couple of things that we can do calculations with for colligative properties. One of those is vapor pressure lowering, which we will not cover that concept. The second is freezing point depression, which we will cover. And the third is boiling point elevation. Oh, and last, osmotic pressure, but we're not covering that one either. Okay, so how are these things important in our everyday lives? Well, number one, the freezing point depression is something that's very important and critical whenever we're dealing with snowy or icy conditions. So they use certain substances that really help with depressing that freezing point below 0 so that pure ice or snow can now melt because we have adjusted and changed the freezing point temperature to be below 0. So therefore it will begin to liquefy as we salt the roads. Alright, just covered that. Okay, Now, so what's going on? We really want to look at the molecular level, what's happening here. If we look at the solution on the left, this is pure water. All right, so if we see here, you see how all those particles line up with one another based on the positive and negative end that we talked about, the partial, because the water is a polar substance, so those hydrogens will face the oxygens because it's a plus and minus end. Well, what happens when I add something like salt to water is now those particles start sitting in between those intermolecular forces, which is what they are. We've not had a chance to discuss that yet. And they're sort of breaking, that intermolecular force, which is a type of bond, but it's between those materials. What happens is that now weakens that solution. It can't behave the way that it normally would when it's pure form on the left. Okay, so the freezing point depression, we have constants that have been created to go with our formula. So pure solvents each have their own Molau freezing point constant. We're going to be working luckily with mostly water. We might have some that have a different type of solvent like an alcohol, and I'll give you the constant for that as needed. But in general, we're really going to work with whatever the Molau freezing point constant is that has been predetermined for water. Okay? What does a freezing point constant represent? It represents the freezing point depression of the solvent in a 1 Molau solution. And what it does is it provides us with the amount that the freezing point is lowered for every 1 Molau concentration solution that I have. And water's is negative 1.86 degrees Celsius per Molau. Right, so we're going to use this in our formula. Again, if it wasn't water we were discussing, I would have some different constant that was already predetermined. Okay, so let's go ahead and look at a problem and see how we might need to solve that. But first we're going to need a formula so that we can deal with that. So, freezing point depression, what that means is how much am I depressing the freezing point below 0 degrees Celsius for that solvent, which in our case is going to be water. So we use a delta T subscript F, okay? So that is the change in the freezing temperature is equal to Kf, which is our constant, times Molau, which is the lowercase m, times N, which stands for the number of moles. In most cases, it will be 1. In many cases, it will be 2 or 3. Okay, so I just went over those variables with you. Delta Tf is the freezing point depression. Kf is our constant, which in general will be negative 1.86 degrees Celsius per Molau. And then M stands for the molality, and N stands for the number of particles that are making up that solute. Oh, and you know what? I think I want to stop here, but I want to talk with you just briefly. And I forgot. That's so funny. Okay, I'm going to continue in just a moment, okay? Thank you very much.